Hello, welcome back. In the last video, we talked about rotary embeddings. In this video, we're going to talk about quantization. So for KV, after we apply the rotary embeddings, you'll notice that we do this. And you'll also, if you remember, in the last video, we talked about how we actually don't apply rotary embeddings on all of KV. We only apply it on the last RD elements. So the first elements before RD, we actually do not apply positional encodings. And so Deepseek v4 does QAT, which stands for quantization aware training. And what this means is that in training, even though this KV tensor is in BF16, they actually simulate what the values are had you downcasted it to FP8. And the reason is so that at inference time, when you write your really efficient inference kernels, you can actually just write FP8 kernels, and you won't have as much loss in your performance because during training we kind of already simulated it. So before we get into this code, let's build some intuition. So before I kind of really understood quantization, my first question was always, well, why don't we just do this? Why don't we just take X and then downcast it to FP8? And the reason is, as you see here, if you just naively do this, what you end up having is this dynamic range problem where, if you have 0.01, 0.02, they both become 0, and you've lost all the nuance. And so in practice for quantization, we do kind of more clever things where, we might take the maximum element of the block and then we might scale it. And then that way you end up with, you end up keeping a lot more of the information in your quantized tensor. And for transformers, you might have these hidden dimensions where different blocks actually need different scales. And so if you had a global scale, you might just destroy certain blocks. And so by having a block level scaling, you can get nicer quantization effects. Now with respect to performance, this quantization method is actually a lot of operations, and each one of these operations will launch kernels, they'll read memory, and they'll write memory back to HBM. And so there's a lot of overhead to do this as separate kernels. And so this is why in practice, for quantization, we'll write these fused kernels where we do all of this in a single kernel. So going back to this, you can see that activation quantization is defined in this kernel module over here. And you can see that indeed we basically call this actQuant kernel, and it does all of the math we talked about earlier in a single fused kernel. So yeah, hopefully that was interesting. We're going to dive more into kind of the interesting parts, like the compressor and the indexer in the next video. So see you there.